Good morning, and Andrew, thank you for the introduction. As mentioned, the sort of central theme of my presentation today is pertaining to dynamic transfer functions for modeling and simulation of dual porosity systems. Before I dive into the details, I want to talk a little bit about the Energy Simulation Research Chair at USC, of which I'm one of the co-chairs, jointly with Dr. Jathapur, who's going to present next. And I'm showing you sort of our initial thinking of how our efforts and activities would fit into this energy simulation world. So if you have seen any of my talks before, you've probably seen this slide as well. But it captures pretty well our sort of ideas on how to drive forward simulation technology, in the sense that we need to be fully aware, or to the extent possible, of errors that we make when we apply simulation tools in engineering subsurface resources. And we can think of it as a simple little process where we have some inputs, and we are affected by some sources of errors that we have. And one is the parameters that we put into our simulation tools, and that is sort of on the side of what Dr. Jathapur is working on. While on my side of the activity, I look at the physical processes and to see if we represent them adequately to make good engineering decisions based on existing simulation technology. None of these two will stand alone, and we need to make sure that we try to balance the errors that we deal with when we try to predict what happens in a certain subsurface operation. Now, a little on the research activities under the advanced forecasting activities. We are working primarily on unconventional oil and gas resources, and we look at things related to how we characterize these materials from core scale to pore scale and so forth. And we study dynamics, if you will, of mass transfer and absorption in these type of resources that are there. In addition, we are also looking at how the materials interact with the fluids that we are interested in engineering out of the subsurface, including how things may change around when we confine fluids in very small pore spaces. Now, in addition to sort of the more fundamental studies, we look at applications thereof in terms of enhanced oil and gas recovery. Again, this is with emphasis on mass transfer in unconventional resources, including but not limited to how do mass transfer occur across gas-liquid interfaces when we are trying to design enhanced recovery techniques. And one of the mechanisms for that is diffusive mass transfer, and one can argue for and against its importance, but it's critical that we understand the role of diffusive mass transfer in enhanced recovery operations. And finally, diffusion is coupled to phase behavior, and phase behavior is affected by tight systems. So all these things are tightly coupled, which makes the overall process more complex. And we work hard to try to design experiments and modeling exercises where we isolate effects of the individual aspects. Now, the overarching approach is that we combine experiments with modeling to sort of delineate these complicated processes. And step two is to translate models that we find sufficiently accurate into efficient algorithms that we can use for simulation applications, for instance. Okay. Now, today I'm going to zoom in and talk a little bit about transfer functions in dual porosity systems. And the background and objective here is based on the observation that the sustained increase in production of oil and gas in the US, for sure, is hinged on the continued development of tight oil and gas resources. Okay. Now, and once we go there, we'll find that a bulk of the production that will come from systems that are fractured, either intentionally or unintentionally, and of, I call it, increasingly modest permeability. So increasingly low permeable settings. So for us to be successful here, we need to make sure that we have accurate technology for modeling simulation that feeds into optimization of production operations. So as I mentioned, I'll take a closer look at some aspects of dual porosity modeling today inside systems, and ask the question if I think we are accurate enough. And I'll give you a hint. It's not yes. Okay. Now, a very basic introduction to the concept of dual porosity modeling. I know it's Friday, so we take it easy. Is just the idea of having two continually interacting through some mechanism. Here I show a simple, let's say, block of matrix-type rock that interacts with fractures all around it, and we have PF matrix pressure, PF fracture pressure. Now, the transfer between matrix and fracture can be described directly with single porosity modeling and get final solutions, but we have worked for many years with ideas of dual porosity representations, where we look at an average response of what is inside the matrix block as a function of time through the application of transfer functions. And in the simplest form, we can write it like this, where the transfer depends on a shape factor, a term here that includes permeability and fluid characteristics, and then a driving force between the fracture and the matrix. The key here is the average. Okay. Now, if we look at the literature dating back from Barenblatt, Wallenroot, Cassini, and so forth, there are numerous suggestions on how to calculate the shape factor correctly. And just a quick reminder, shape factor is trying to tell us what is the surface area of interface between matrix and fracture per bulk volume and a characteristic length. So the unit is 1 over length squared. And oftentimes we use them as constants in simulation tools. It can be different constants for different sections or different blocks, if you will, but we keep them constant in time. We also treat them as history matching parameters sometimes if you go there. So there's, and yeah, there's a lot of literature out there that's very interesting to read, but it's essentially focused on getting the coefficient right. Okay. Now, the question I asked today is, well, what about the transient inside the matrix? Because we claim to have some idea about that when we write a transfer function like this, and we define it in terms of an average over the block. So let's take a look at what people did to try to factor that in. Limenassis came up with a nice idea of just using analytical solutions to here simple geometries, planar, cylindrical, and spherical geometry, representing 1, 2, and 3 sets of fractures, respectively. Now, if you look up in your old math book by Crank, you can find series solutions for the average response in pressure here relative to its initial pressure and the boundary condition pressure here, if you will, as a series solution. Now, if we follow the approach of Limenassis, we say, okay, the second and third and so forth terms of this summation dies out pretty fast with increasing time, okay, actual physical time t. And that would leave us with a single term, an exponential function that would allow us to represent or approximate the change in the average pressure inside a given geometry as a function of time, given relevant physical properties. Okay. Now, to get this into a form that is useful for us, we would have to differentiate it with respect to time, and then use this equation again to eliminate time itself. And then we get two things. We get a shape factor for free, defined by an approximation to the dynamics, which is good. So we try to sneak the physics into the shape factor, what's happening. and we get values of shape factors shown here for different geometry, pi squared, almost 2 pi squared, almost 3 pi squared for an isotropic and a cubical matrix segment. So LSM on all sides. And that departs a bit from what Warren and Root told us that we should use for shape factors. And there's, if you generate a table, a lot of different versions. But the approach here seems pretty solid because the dynamics of this transfer function that you get from this exercise integrate ingredients of the dynamics. And that is what we're looking for here to get it right. Now, so the question to ask is that if we go with a truncated series solution to formulate our shape factors and transfer functions, will they break down in some parts of the parameter space that we're operating in? And I show a very busy table here that effectively gives a column for different settings. We have conventional resources defined by fluid compressibility, fluid viscosity, and so forth. We have one for tight oil systems and one for shale gas systems. Now, the key important factor here is that we can calculate a diffusivity based on the parameters that we see here. And we can see that for a conventional setting, conventional reservoir here, which is, millidarcy range, no, sorry, here, 10 millidarcy, this is a microdarcy, and this is 10 nanodarcy. And we see that the characteristic time that we get from the diffusion coefficient and the characteristic length varies substantially across these different types of applications, from extremely fast to a couple of months. For this is, mind you, a matrix block that is 10 foot on each side. Now, if we look at, this is a figure that I lifted from the paper of Vermeulen that compares the analytical solution with, the circles with the first term approximation that is given by the solid line. We observe there's a departure at early time. And down here is really the dimensionless time. Dimensionless time is just physical time divided by our characteristic time. And we see that the two, the analytical solution and the approximation start agreeing about a dimensionless time of 0.8. Okay? And that may say, that's nothing, dimensionless time is fine. But if we go back and we say, okay, fine, we know the characteristic time, we know the dimensionless time where things start lining up. We see that depending on the application, it could range from not a problem at all, basically immediately catch up between the approximation and the true solution for conventional resources to 2 months for a shale gas system before they catch up. And it's worth noting that production from these type of settings is related to the slope of this curve. This shows the normalized pressure. Gradient in pressure tells us what production rates that we can expect. Okay, and we note that the slopes of these curves are dramatically different at early times until they start agreeing after a certain dimensionless time. Now, the key here to note is that we define the characteristic time in terms of the inverse of the shape factor times the diffusivity that represents the process at play. Okay, and working with dimensionless time can be convenient for comparing results, but it can also fool us a little bit because it looks pretty good. However, we would expect disagreement for the first 2 months of production from this particular approximation. So, what do? Well, we can take a look at the approach that was introduced by Vermeulen in 1953 for a completely different application. That was in chemical engineering, and basically using an approximate solution to spherical geometry, a diffusion in spherical geometry, catalyst calculations, I believe. He could use a simplified closed form solution that captured the dynamics of on average inside the domain of interest. Now, so here instead of concentration, you can think pressure, and then everything else will be the same. We have here a diffusivity, and we have a shape factor built in. In this particular case, it would be pi squared over r squared. This idea was sort of used in subsurface flow settings by Zimmermann back in 1993, where he used this form which is limited to handle spherical geometry only. Okay? Now, if we take it a step further, we can say, well, we could generalize this functional form and use that to have transfer functions that do not approximate or truncate the analytical solution. And here I just write it in a general sense. Y is the normalized, let's say, change in the average property that we're interested in representing inside the matrix segment. And we have sigma d here, which is 1 over the characteristic time. So it's a function of the dimensionless time only. Okay? Now, sigma, which is our shape factor, and v, which is a model parameter, have to be determined based on the geometry of interest to us. But before we even start talking about this, we can rewrite the change in the normalized average. Again, we differentiate this with respect to time and eliminate time itself. We can find that change in time of the average quantity, which is our transfer function, based on our inverse of characteristic time, model parameter v. Beta is defined over here, and then our usual driving force between fracture and matrix. Okay? Beta here is a correction that we get because we want to recover the functional form that we're all comfortable with, and we get that as a function of the fracture pressure, initial pressure, and the current status of affairs inside the matrix, plus then our model parameter v. Okay? Now, this type of transfer function can be applied for a range of physical processes. For viscous flow, d would be defined based on permeability, porosity, viscosity, and fluid compressibility. If you had a diffusion process, well, we have diffusion coefficient. If you have heat conduction, well, we have thermal diffusivity as well. And this is just showing the value of the parameter as represented up here. Now, the application, well, pressure response of viscous flow, tight oil gas systems, diffusion coefficients, well, unconventional oil, enhanced recovery from unconventional oil systems, and temperature variation. Well, if you're looking at fractured geothermal systems, this might be a very useful formulation as well. Now, let's get the parameters for the new or generalized transfer function. And what we took here is just 3 simple geometries, planar, cylindrical, and spherical, representing 1, 2, and 3 sets of fractures. And if we do that, we can estimate a shape factor here. It's just scaled with the length squared, because we're using a, let's say, a single block of matrix, same length on each side. But that can, of course, be relaxed following the literature on how to factor in if you have slightly different geometry. But we'll get back to that. Now, v that we get, the factor here, is representing each of the geometries, and it's just a model parameter. Now, to test this idea, we implemented the new transfer function into the dual porosity black hole model of MRST, which is the Matlab Reservoir Simulation Toolbox that is primarily developed by SimTef. And we used in particular the dual porosity model that was developed by Sebastian Geiger's group at Harvard. Thank you very much for that. And we implemented that to see how the model would compare to traditional representations such as the transfer function of lim and assist, which is popular in simulation tools. Let's jump into it and look at some results. We pick a simple model here, just dry gas. The domain we have is 1,000 by 1,000 by 50 feet, and we divvy it up in a number of matrix blocks. Fracture porosity is lower than the matrix porosity. We have a fracture permeability of 10 millidarcy, and we start with relatively high pressure. It could be, it could be in the permanent basin. We do get substantially high pressures, and we set the bottom hole pressure of a single well that sits in the center to 1,000 psi. And then we see what happens if we change the matrix permeability. So we can start here with a microdarcy, a tenth of a microdarcy, and this one over here is 50 nanodarcy. So we go from A to C and we make it increasingly tight in terms of resources that are explored. So we compare here the response in terms of average pressure in the entire reservoir model for different values of permeability. We show the calculation results of the new transfer function that we call G Vermeulen here. So sorry to him, and with the transfer function that Lyman Assist suggested. And we see for moderate permeability of the matrix, we don't see any difference. Okay, and that is because it's a fast process. So a dimensionless time of 0.8 doesn't mean much here. It's a very short wall time period, if you will. As we decrease the permeability, we start to see the two models depart, and a difference building up here, particularly at early times. And as we go to 50 nanodarcy, we can see that even at 100 days, we actually have substantial difference between the average pressure in the reservoir models, okay? Which amounts to 1,000 psi. Now, this is the gap that we see, and this is raise the question: what if this had been a wet gas or a condensate system, and I would happen to have a dew point lying around up here? I would mispredict, or I would have conflicting information about when would I start having liquid forming in subsurface. So we need to take a closer look at that, and we'll get back to that in just a second. Now, before before we claim too much, we had to go back and compare with commercial tools. So we compared MRST with ECLIPSE and GMG. This was for the black oil single block calculation. We used a single porosity model with 50 by 50 cells, just 2 sets of fractures, or the DP model. And what we see here is that we line up all the different tools. ECLIPSE agrees with CMG, and CMG agrees with MRST, and MRST agrees with ECLIPSE, so everybody's happy. This is, we resolve the transient inside the matrix block because we're using a single porosity representation. Now, as we go to dual porosity representation over here, the picture change. All the dual porosity models are based on the function introduced by Lyman Assist, which are available in all the commercial tools, and they all agree. This is the behavior we should get. However, if we use the new formulation, we see a substantial departure by the gray line, particularly at early times. Early times here is up to 500 days. Okay? Now, if I take this gray line and I show it as simples over here on the single porosity model, we see that the dual porosity representation of with the new transfer function agrees with the single porosity fine scale solution of the commercial tools. And the commercial tools do not agree with their own single porosity representation of the same process. Okay. Now,
Dr. Jessen, can you wrap up in about 2 minutes?
Yes, I certainly can. We did the same with the sector model, found similar behavior. And then we said, okay, fine. I mentioned condensate information, and we extended the capabilities of MRST to include compositional dual porosity modules. That was a bit of work, and the students on that really deserves a lot of credit. So I'm just going to show you a quick example, and then I'm going to wrap up. So the condensate system is a simple 4-component system, which is primarily methane, got some butane, some decane, and a slight tad of CO2 in there. Now, this condensate system behaves like they always do. If you, depending on where you are in temperature, you will see liquid dropout as you go below the dew point. That is about 3,200 psi here. I'm going to look at the blue curve here, where we have about 12% liquid dropout, which should substantially interfere with the flow in the condensate system. And I have a slate of modeling parameters. I do a single block calculation over here, 20 by 20 by 20 feet, 0.1 microdarcy, 20% porosity. I start at 5,000 psi and deplete at 2,000. And here I just use a single set of fractions. Rel perms, and here we go. If we look at the average pressure inside the block, we can see that, again, same behavior. The single porosity representation and the modified transfer function are in good agreement, while the standard representation here fails to capture the single porosity solution. Over here we see the pressure of transient inside at the end of the simulation, 30 days, and below we see the saturation where liquid is building up at the interface between the matrix and fracture here, and where we'll start having relative permeability effects reducing the flow. We can look at normalized production rate, and we can now look at cumulative production, and they all show the same picture, that there is a difference at departure between traditional shape transfer functions and the dynamic one that we've introduced here. So, summary: tight oil and gas hold substantial resources, and modeling and simulation of fracture system will become increasingly popular. We've found a lot of contributions on how to calculate the shape factor, and also recently on how to represent the fracture geometry, but less effort in terms of understanding what is the transient inside the actual matrix. We introduced this generalized formulation, which extends the idea of Zimmermann 1993 to general geometry. We can get those parameters for the new model from analytical solution, or refine single-phase single porosity calculations for pretty much any geometry that you would like. So we have a simple way of representing subscale gradients in dual porosity model and promote more accurate simulation of production here. We tested it in the open source MRST, and we looked also at how it compared with commercial simulation tools. We agree if permeability is high enough. If permeability gets low, there's a departure between the calculations that we get between using different representations of the mass transfer and out of the blocks. Now, we showed that traditional formulations, they can misrepresent the pressure transient and of course the production then, if the permeability is removed to sub-microglass. And finally, we developed this new module for MRST, so we can start studying compositional behavior. Let me wrap up with a few words on what's next. Well, since we now have this new capability of dual porosity compositional modeling, we will move forward and investigate performance of new transfer function for irregular geometries, including geometry, anisotropy, etc. Integrate and investigate the role of competitive sorption when we are looking at tight gas production, and also implement and investigate the role of diffusion during EOI and tight operating systems. Finally, as a reach out to audience and others, I would really like to explore how we model heat transfer also in fractured geothermal systems, because it's identical in mathematical form to a pressure transient or a diffusion process in a fractured system, and we can use the same ideas as I discussed here. With that, I just want to acknowledge the support to the activities here in the simulation, Department of Energy, Basic Energy Sciences, Chevron, Saudi Aramco, and of course also the School of Engineering at USC. And also thank the students who are actually doing all the work. With that, I would be happy to take any questions.
Okay, Dr. Jessen, I only have time for one question. I would ask a question from Dr. Russell Johns at Penn State University, who's a former energy simulation research chair.
Yes.
He certainly agrees with you that diffusive transport is important for ultra-tight rocks. Are you able to incorporate both diffusive and advective transport in the transfer function? That is, transport may be the result of several mechanisms.
Yes, so that's a good question, and the way that we can approach this is basically to split up the two phenomena and say, well, we can have a transfer function that handles the viscous flow, if you will, and a transfer function that happens that takes care of the diffusive mass transfer. Now, if that, if there's a coupling between the viscous flow and the diffusion inside the matrix block, that will have to be addressed separately, and I have not looked at that quite yet. But I'll be happy to collaborate with Ross on that if he's not too busy.
Okay, thank you very much.